When can humanity's spacecraft become fast enough for us to leave the solar system, the galaxy, and explore the entire universe? The vastness of space is filled with countless unknowns. Humanity's desire to explore the stars is hampered by the slow speed of our spacecraft. To address this, various interstellar travel strategies have been proposed, starting with the gravity assist maneuver. Gravity assist is a mature and widely applied technology. It remains a reliable and indispensable tool for future, longer journeys. The principle of gravity assist is relatively simple. It borrows energy from planets. A planet's rotation and orbit endow it with immense angular momentum. In the solar system, the Sun holds only about 2% of the total angular momentum, while the other 98% resides in the celestial bodies orbiting the Sun. When a spacecraft enters a planet's orbit, it can gain a portion of the planet's angular momentum. This transfer increases the spacecraft's speed and alters its trajectory as it exits the planet's gravitational field. According to the law of conservation of energy, while the spacecraft's kinetic energy increases, the planet's kinetic energy decreases slightly. However, because planets have enormous kinetic energy, the minuscule portion gained by the spacecraft does not affect their motion. This is akin to harnessing energy from wind using turbines without worrying that the wind will stop blowing. As early as 1982, Voyager 1 and Voyager 2 utilized a rare alignment of 9 planets, leveraging the gravity of Jupiter, Saturn, and Uranus for efficient interstellar exploration. For instance, Voyager 1 used Jupiter to propel itself to Neptune, becoming the probe to study the most planets. In 1992, the Ulysses solar probe used Jupiter's gravity to turn 90 degrees, successfully entering the Sun's polar regions to study the previously unexplored solar poles. Cassini, launched in 1997, also employed gravity assists. Although Saturn is only 1.25 billion kilometers from Earth, Cassini's journey covered 3.2 billion kilometers because it performed 2 flybys of Venus and additional flybys of Earth and Jupiter before heading to Saturn. Similarly, the New Horizons probe launched in 2006 used Jupiter's gravity to reach Pluto, significantly shortening its travel time. Gravity assist can drastically reduce interstellar travel time. For example, without gravity assist, using the most economical Hohmann transfer orbit, a spacecraft would take 6 years to reach Saturn, 16 years to Uranus, and 31 years to Neptune. With Jupiter as a gravity assist, the time to Saturn is reduced to 3 to 4 years, to Uranus 8 to 9 years, and to Neptune 12 years. However, gravity assist has its limitations. It requires precise timing and calculations to align the spacecraft's trajectory with the orbit of the assisting planet. This restricts its flexibility and initiative. Light, as a form of radiation, can we harness it as a driving force? Can we use light as propulsion? The answer is yes. Over 400 years ago, Kepler envisioned exploring the stars with a sailboat, speculating that a weak solar wind pushed the tails of comets. While his explanation of the solar wind was later proven incorrect, his vision inspired scientists to discover that sunlight can exert enough force to move objects. In 1921, Russian spaceflight pioneer Konstantin Tsiolkovsky proposed the concept of the solar sail. In 1963, Arthur C. Clarke popularized the idea in his science fiction novel The Wind from the Sun. By the 21st century, solar sail spacecraft became a reality on the big screen, such as in Star Wars Episode II, Attack of the Clones, where Count Dooku's vessel features a solar sail. Although sunlight's force is weak, its advantage lies in its persistence. As long as there is sunlight, a solar sail can slowly accelerate under solar pressure. By adjusting the sail's angle relative to the sun, we can control the spacecraft's speed and direction. Over time, this acceleration can lead to astonishing speeds. For instance, a solar sail spacecraft with a 70,000 square meter sail and a mass of 500 kilograms could increase its velocity by 1 millimeter per second after leaving Earth orbit. At this rate, it would reach Mars orbit in 284 days, surpassing the speed of current rockets. By the time it reached Mars, its speed would have reached 24.5 kilometers per second, 88,200 kilometers per hour, far exceeding the third cosmic velocity achieved by New Horizons. Solar sail spacecraft are no longer just theoretical. On June 21, 2005, the Cosmos 1 solar sail spacecraft, jointly developed by the US and Russia, was launched from a Russian submarine in the Barents Sea using a Volna rocket. Composed of 8 triangular blades with a total area of 600 square meters, the sail was thinner than a standard plastic garbage bag, yet incredibly strong and coated with highly reflective material. Unfortunately, the rocket lost contact with the ground 83 seconds after launch. This failure did not extinguish hope. In 2010, Japan's Ikaros solar sail successfully launched and flew to Venus. Its square sail, with a diagonal length of 20 meters, was made of polyimide resin material just 0.0075 millimeters thick. Ikaros completed its mission, demonstrating acceleration and orbit adjustment using sunlight, proving the feasibility of solar sail technology. Solar sails are suitable not only for interplanetary missions but also for interstellar probes. With low cost and high speed, they are the preferred choice for reaching interstellar space under low-tech conditions. However, solar sails face significant challenges. A single photon carries minimal energy, and even sunlight's radiation pressure on a football field-sized sail is comparable to the weight of a sugar cube in your hand. To achieve high speeds, extremely large sails are required. Moreover, sunlight dissipates significantly beyond Jupiter's orbit. To address these issues, scientists have proposed laser-driven light sails. Though artificial lasers are less powerful than sunlight, they do not dissipate and can concentrate all energy on a single point. By positioning laser emitters in Earth orbit and targeting the sail, interstellar travel becomes possible. This led to the ambitious Breakthrough Starshot initiative. The project envisions using advances in nanotechnology, microelectronics, and optoelectronics to create a chip-sized probe attached to a 4-meter-wide light sail. Using laser-generated pressure, the probe could be accelerated to 20% the speed of light in a short time. However, laser-driven spacecraft face significant challenges. The immense laser array would require power equivalent to several nuclear power plants. Precisely targeting a small sail several light-years away is an extraordinary task. A proposed solution is to place the laser array on the Moon, which is rich in helium-3, an ideal nuclear fusion fuel. If controlled nuclear fusion becomes feasible, lunar-based lasers could propel light sails into deep space. In summary, while the prospects for light sail spacecraft are promising, Even if all these visions are realized, light sails have a fundamental flaw. They rely on externally constructed laser arrays on Earth, the Moon, or other celestial bodies. This external propulsion is inherently unstable, easily obstructed by asteroids, interstellar dust, or other objects. Therefore, humanity must continue to explore and innovate, seeking more reliable and efficient means of interstellar travel in the future. Exploring the vast universe, how spacecraft achieve self-breakthrough is a core issue that urgently needs to be addressed in the field of aerospace. The limitations of chemical fuel make it difficult to support long-term, long-distance space travel, prompting scientists to focus on nuclear-powered spacecraft. The concept of nuclear propulsion can be traced back to 1944, when Manhattan Project scientists Stanislav Ulam and Frederick Hoffman first proposed the idea of a nuclear-powered spacecraft. Subsequently, the U.S. Atomic Energy Commission and NASA jointly launched the NERVA project, Nuclear Engine for Rocket Vehicle Application. This project aimed to develop nuclear thermal rockets, whose working principle involves using a nuclear reactor to generate heat through nuclear fuel, heating the propellant flowing through the reactor, and producing thrust by expelling it through a nozzle. Hydrogen was selected as the primary propellant and coolant for NERVA due to its excellent thermal conductivity and the ability to absorb significant heat when dissociating into hydrogen atoms at high temperatures and low pressures. Its extremely low molecular weight made it an ideal propulsion medium. Between 1955 and 1968, a series of nuclear rocket engine tests were conducted at the Nevada test site, resulting in a nuclear rocket engine weighing approximately 200 kilograms and generating up to 100 tons of thrust. In theory, such an engine could enable astronauts to reach the Moon within 24 hours. However, with budget cuts to the Apollo program in the 1970s, plans for extended manned lunar missions and manned Mars missions were indefinitely shelved, and the NERVA project was cancelled in 1972. Nevertheless, the suspension of this program did not halt further exploration of nuclear-powered spacecraft by scientists. Robert Zubrin, a renowned aerospace engineer and advocate for manned Mars missions, proposed a new concept called the nuclear saltwater rocket. This rocket uses saltwater containing dissolved uranium-235 as fuel. Heating the radioactive saltwater triggers nuclear fission reactions to generate thrust. In this design, water serves both as the propellant and as a neutron moderator. However, the waning enthusiasm for space exploration in the late 20th century meant this concept did not receive widespread attention. Regardless of the propellant, whether hydrogen or saltwater, all propellant-based nuclear rockets face an unavoidable challenge: dependence on propellant. Propellant consumption limits the spacecraft's range, preventing it from venturing far from supply stations. This predicament is akin to the steam locomotive era, where trains could not travel far from water stations. As a result, propellant-based spacecraft are mostly confined to the solar system, relying on planetary bases for support. This challenge inspired the concept of propellant-free nuclear fusion rocket engines. Under current technological conditions, controlled nuclear fusion is primarily achieved in two ways, corresponding to two types of fusion rocket engine designs. The first is the magnetic confinement fusion engine. Magnetic confinement fusion heats nuclear fuel to millions of degrees, forming a plasma state and enabling nuclei to collide. Since plasma is charged, it can be confined using strong magnetic fields. Otherwise, the high-temperature plasma would melt any container. While magnetic confinement fusion may be ideal for nuclear power generation on Earth, it is less suitable for spaceflight. Confining high-temperature plasma requires a magnetic field generator consisting of permanent magnets and electromagnetic coils, which are bulky and heavy, necessitating an extremely large rocket engine. The second is the inertial confinement fusion engine, also known as pulsed fusion. This technology uses lasers or particle beams to irradiate nuclear fuel pellets, producing extremely high temperatures and creating plasma with a density higher than that of magnetic confinement fusion, thereby triggering nuclear fusion. Due to the short reaction time, the inertia of the small fuel pellet itself can maintain sufficient heat for the reaction without requiring strong magnetic confinement. In the vacuum of space, particle beams have a clear advantage over Earth-based applications, as they are not hindered by atmospheric molecules. This approach seems more feasible. However, inertial confinement still requires laser or particle beam generators and energy supplies. Even so, this design is likely much lighter than magnetic confinement fusion engines. In fact, as early as half a century ago, the concept of the centipede-style nuclear fusion propulsion spacecraft was proposed. In 1970, American scientist Friedwert Winterberg proposed using high-energy electron beams to induce nuclear fusion. His rocket engine design released about 10 billion joules of energy per fusion event, achieving speeds of 300 kilometers per second, equivalent to 1.08 million kilometers per hour. This fusion rocket included a combustion chamber formed by magnetic fields. Nuclear fuel pellets would be fired into the chamber and subjected to electron beams, generating high-temperature plasma as the source of thrust. This approach eliminates dependence on propellant. While breaking free from propellant constraints is a significant advancement, nuclear fuel remains an inherent limitation. Achieving freedom from fuel constraints would be even more ideal. But is this possible? Theoretically, it is still feasible. Thus, two innovative solutions have emerged. The first is the antimatter-fueled spacecraft, a design that does not entirely eliminate the reliance on traditional fuel. It is known that when particles and antiparticles meet, their entire mass is converted into energy according to Einstein's mass-energy equivalence equation, with an energy conversion efficiency of 100%. In comparison, atomic bombs have an average energy conversion rate of only 1%, and hydrogen bombs achieve just 2 to 3%. Thus, merely 1 gram of antimatter can release energy equivalent to the Hiroshima atomic bomb. Theoretical calculations suggest that a spacecraft weighing 1 ton and carrying 20 kilograms of antimatter fuel could reach an astonishing speed of 130 million kilometers per hour. However, antimatter is extremely scarce in nature and can only be produced artificially. Currently, using the Large Hadron Collider in Europe, antimatter can be produced at a cost of hundreds of trillions of dollars per gram, limiting its application to scientific research. For interstellar travel, this remains unattainable as fuel. Nevertheless, scientists believe that in the future, by applying 10 to the power of 29 watts of power to a single point in a vacuum, a capability near the energy output of a Type II civilization, it may be possible to induce vacuum breakdown effects and convert energy at a specific point into particles and their corresponding antiparticles, thus producing antimatter. However, it is important to note that antimatter particles produce massive explosions upon contact with matter, requiring magnetic confinement for antimatter fuel and remote-controlled use as a propellant. Currently, the world's most powerful laser weapon achieves only about 10 to the power of 16 watts, falling 13 orders of magnitude short of the energy required for antimatter spacecraft. Even so, the technology to create antimatter from a vacuum marks humanity's first step toward the stars. Although we often say that the universe is a vacuum, it is not entirely empty. It is filled with an extremely sparse gas known as interstellar matter. While its density is incredibly low, with only 1 atom per cubic meter, it is still something. If this omnipresent interstellar matter could be harvested as fuel, a spacecraft's range could theoretically become infinite. Based on this idea, in 1960, physicist Robert Bussard from the Los Alamos Laboratory in the United States published a paper titled Interstellar Matter and Interstellar Flight, proposing a groundbreaking propulsion method for spacecraft. He envisioned a funnel-shaped collector mounted at the front of the spacecraft, which would use a massive electromagnetic field to collect hydrogen from interstellar matter. During high-speed travel, the hydrogen would be compressed into a nuclear reaction chamber under the influence of the magnetic field. Once the temperature and density met the conditions for nuclear fusion, energy would be released. The principle was to use hydrogen as the fuel for a fusion engine. The faster the spacecraft traveled, the higher the collection efficiency, much like how a blue whale filters plankton with its wide-open mouth. The funnel at the spacecraft's front would draw in interstellar matter, channeling the energy it generated toward the exhaust direction of the engine, propelling the spacecraft through reactive force. This design eliminates the need for onboard fuel and reaction mass. Only a small amount of initial fuel is required, as the rest is collected in flight. This engine later became known as the Bussard ramjet. Theoretical predictions suggested that if the spacecraft maintained an acceleration of 10 meters per second squared, it could reach 77% of the speed of light in less than a year. However, there was widespread skepticism about its practical application. According to Bussard's calculations, achieving the desired 1g acceleration for a 1,000-ton spacecraft would require a collector with an area of 10,000 square kilometers. If constructed from a polyester film just 0.1 millimeters thick, the collector would have a mass of 250,000 tons. Even with advances in materials science, such a design remains a formidable challenge. Moreover, Bussard assumed that interstellar matter was ionized, carrying an electric charge that could be captured by the magnetic field. However, in reality, most interstellar matter consists of neutral atoms and molecules, which are nearly unaffected by magnetic fields. High-powered lasers would be needed to ionize hydrogen atoms in the spacecraft's path, transforming them into single protons that the magnetic field could capture. With this approach, the collector could be designed as a mesh rather than a solid structure, significantly reducing its physical mass, provided the magnetic field coverage was sufficiently large. Despite the enormous potential of the Bussard ramjet concept, its implementation faces a series of severe challenges. First, the energy required to generate the lasers and magnetic fields is enormous, and this energy must be prepared in advance. Second, the magnetic funnel's mechanism is far more complex than anticipated. The magnetic lines of force converge at the funnel's entrance, causing incoming charged particles to be repelled rather than captured. This mechanism limits the collector's efficiency, as particles within the cone-shaped area in front of the spacecraft cannot enter the reactor, thereby reducing energy conversion efficiency. To address this challenge, scientists have proposed using pulsating magnetic fields to mimic the process of opening and closing a mouth to capture particles. However, this approach also faces numerous practical difficulties and requires further technological breakthroughs. In addition, the collected particles are mostly hydrogen ions, which are not as easily fused as some other elements. This limits the fuel efficiency and performance of the Bussard engine, making it unlikely to achieve its full potential in practical applications. Finally, the Bussard ramjet is constrained by the spacecraft's speed. The collector can only gather sufficient fuel for the ramjet engine to start when the spacecraft reaches a certain velocity, approximately 6% of the speed of light, which is a very high threshold. Consequently, an initial booster engine would be required to bring the spacecraft to the ignition speed of the Bussard engine, and reaching this speed is itself a significant technical challenge. Additionally, interstellar dust and charged particles pose serious threats to a spacecraft traveling at high speeds. These particles could generate high-energy particle showers, potentially causing catastrophic damage to the spacecraft. Calculations show that a 1-kilogram object moving at 30% of the speed of light carries the kinetic energy equivalent to 1,000,000 tons of TNT. Thus, a spacecraft traveling at sublight speeds could be constantly subjected to impacts comparable to hydrogen bomb explosions from collisions with stationary dust particles. Despite these immense difficulties, the Bussard ramjet remains a favorite of science fiction writers. Its appeal lies in its reliance on known technologies to achieve near-light speed travel. American sci-fi author Larry Niven depicted its use in his Known Space series, where humans initially employed Bussard-powered automated probes for interstellar colonization, while the wealthy used it to move their families off the overcrowded Earth. In Ringworld, this type of spacecraft was used for long-distance travel and station keeping. In the Star Trek series, a similar device called the Bussard Hydrogen Collector became part of the matter-antimatter propulsion system. It harvested hydrogen from interstellar matter and converted it into matter and antimatter to power the warp engine. A bolder vision appears in sci-fi writer Poul Anderson's Tau Zero, where a Bussard spacecraft loses its deceleration system due to interstellar dust and enters an infinite acceleration state. As the ship approaches the speed of light, relativistic effects cause time to dilate, allowing the crew to witness the ultimate collapse and dissolution of the universe. The Bussard engine's theory opens up the possibility of near-light speed travel for humanity. The Bussard engine theory has opened the door to sublight speed exploration, but surpassing the speed of light may require another groundbreaking technology, the warp drive. According to general relativity, spacetime can be deformed by mass or specific energy, leading to compression or expansion. In 1994, Mexican physicist Miguel Alcubierre proposed an astounding theory through complex calculations. By expanding space behind a starship, the same degree of compression would occur in front of it. Although the space would eventually return to its original state, this deformation process could generate thrust behind the spacecraft and pull in the front, creating a powerful propulsion effect. This method of propulsion, known as warp travel, makes the spacecraft appear to ride the waves of space itself, with this wave region called a warp bubble. Inside the warp bubble, space-time remains flat, and the spacecraft is not technically moving but is carried forward by the bubble, thus avoiding violation of the speed of light limit in physics. Theoretically, warp travel could achieve unlimited speeds, enabling instantaneous travel to any part of the universe. However, the faster the travel, the more unimaginable the energy required. In the film Star Trek, spacecraft generate a subspace field through warp coils. When the subspace field exhibits asymmetric oscillation and reaches a certain field strength, it forms a warp field, placing the spacecraft within a warp bubble to achieve superluminal interstellar travel. However, the precise technical details remain unknown. Moreover, humanity currently does not know how to trigger such spatial oscillations or how to exit them once triggered. Scientists believe the answer may lie in energy. The Big Bang unleashed an unparalleled amount of energy, causing space to expand rapidly in an extremely short time. Within 10 to the power of -32 seconds, the volume of space expanded by a factor of 10 to the power of 78. An incomprehensible moment that saw space balloon from atomic size to the size of a galaxy. If humanity could harness such energy, stretching space would no longer be an issue. I firmly believe that under conditions of infinitely advanced technology, any event that has ever occurred can be replicated. According to M-theory, the successor to string theory, altering dimensions and stretching space would require 10 to the power of 45 joules of energy, equivalent to converting the entire mass of Jupiter into pure energy, far exceeding the energy levels humanity can currently control. Another potential solution involves exotic matter, a material with negative energy where particles repel like charges and attract opposite charges. Using exotic matter to create a warp bubble would require only 500 kilograms of it to produce a 10-meter diameter bubble, propelling a spacecraft at 10 times the speed of light. Unfortunately, humanity knows nothing about exotic matter. Some theories suggest that dark energy, responsible for the accelerating expansion of the universe, could be this extraordinary exotic matter. However, warp travel is not without flaws. It distorts the space around the spacecraft, potentially exposing its trajectory to enemies in a human-alien conflict. More concerningly, the structure of space is altered during warp drive. If one warp spacecraft were to enter the wake of another, the consequences could be catastrophic. A 2012 computer simulation revealed a phenomenon where particles with energy opposite to that within the warp bubble accumulate at the front edge of the bubble during superluminal flight. These particles not only gather in the front but may also seep into the bubble, causing an accumulation effect. This is similar to how the number of particles increases in front of a hydrogen balloon as its flight distance grows. When the spacecraft reaches its destination and begins decelerating, the massive amount of energy accumulated during the journey would release in an instant. The resulting energy release could destroy anything it contacts. Additionally, particles that have been lingering within the warp bubble pose a significant threat to the spacecraft itself. For instance, if the spacecraft inadvertently exits the warp bubble while traversing a dust cloud, it could face a catastrophic collision. Moreover, if a spacecraft decelerates too close to its target planet, the unintended release of energy could obliterate the planet in an instant. This means that whenever a warp spacecraft returns to its starting point, local inhabitants would worry about potential accidents. Finally, surpassing the speed of light could lead to even more unpredictable consequences. What those consequences might be is something humanity can only discover when that day arrives. Despite these dangers, superluminal warp travel remains an irresistible pursuit for any advanced civilization. The faster we travel, the greater our chances of survival. The faster we travel, the more unknowns we uncover. The faster we travel, the closer we come to the ultimate truths of the universe. Even more astonishing than warp travel is traversing wormholes. Wormholes can be considered folded space, adding an extra spatial dimension to our three-dimensional universe and opening a new path. Although wormholes are not the subject of today's discussion, they undoubtedly represent a cosmic highway for future spacecraft. Humanity's attempts at interstellar travel have never ceased. Our footprints have reached the moon, and spacecraft have successfully landed on celestial bodies such as Venus, Mars, and Titan. Numerous pioneers have orbited or explored the Sun, Mercury, Saturn, Jupiter, and other celestial bodies, bringing us detailed data and breathtaking images. As Arthur C. Clarke once said, "Any sufficiently advanced technology is indistinguishable from magic." The only way to discover the limits of what is possible is to venture beyond those limits and move from the impossible to the possible. Humanity has ventured out of Africa, crossed oceans and mountains, and spread across continents. In the future, the stars will undoubtedly guide us once again to the infinite vastness of the cosmos. Since the first human looked up at the night sky, we have held an ancient and steadfast dream, to cross the sea of stars and conquer the distant and dazzling heavens. We believe that if we dare to journey, no place will remain unreachable. All the elements in our bodies are gifts from the universe. One day, we too will step into the cosmos and explore its origins, future, and ultimate destiny.